Magic doesn't make my curve break right, its spin does. But how can spin make a ball change direction mid-flight?
To answer this question, let's first define Bernoulli's principle, which will be important later. This principle is an observation on the energy conservation of horizontally flowing fluids, like, for example, air. This principle states that as the velocity increases, the pressure decreases, and vice versa. Now let's talk about the Magnus Effect, the reason why our pitch will break. Any spinning object flowing through a fluid, like air, will experience a force perpendicular to its direction of motion and its spin axis. Now let's take this image and imagine it three-dimensionally, a ball rotating clockwise and moving forward. Because the ball is moving forward, the airflow is coming in this direction towards me. That means that the air on the left side of the ball will be fighting the direction of airflow, which will slow it down, and the air on the right will be sped up, because it's going with the airflow. And here we can apply Bernoulli's principle. The air on the left will have higher pressure than the air on the right. And this pressure imbalance is part of the force that will push the ball from the higher pressure region to the lower pressure region, or in this case, from left to right. Bernoulli's principle isn't the only contributing factor to the Magnus force. The other is boundary layers. Boundary layers are a small layer of air in contact with the surface of any object that is stuck. This happens because air has viscosity, which is the property to resist motion. These boundary layers can't stay attached to the objects forever, because they lose energy. When that happens, the direction of the flow reverses and the air molecules separate from the surface of the object. This is called flow separation.
Turbulent boundary layers are high energy, allowing them to stay attached for longer. If the boundary layer on the side of a spinning ball moving with airflow becomes turbulent, it resists separation for longer than the side moving against the air, creating a large pressure imbalance that boosts the Magnus effect. That's why faster pitchers get more break. Higher velocity creates more turbulent boundary layers.